Welcome to springlib.
Hydrogen bond that involves a dipole for the water molecule that has an OH radical with a charge of minus 0.35 times the electron unit, and a hydrogen radical, which is a positive end of the dipole, which has a positive 0.35 E of charge. We're going to develop a model to determine the strength of the hydrogen bond, which is that red, I'll make it red, dashed line, holding one dipole to another within water. So this is an idea of what gives water its bonding strength. What we'll need is the electric potential energy for point charges. Simple expression KQ, big Q over R. So we're going to develop two expressions and look at the interaction between the left water molecule with the right water molecule. And we'll break it into two parts. There is the potential energy of the hydrogen. Okay, so we're thinking about the left molecule sitting in the potential of the right molecule. And we're going to have to come up with two expressions, one for the bonding energy of the hydrogen on the left to the molecule on the right, and another one for the OH part of the molecule bonded to the water molecule on the right. So if we look at the picture, we have two charges, both the same amount of 0.35 E. And we'll write down what E is in a little bit, but it's the fundamental unit of charge. And then the hydrogen is interacting with the OH, which is negative at a distance of what I've labeled as D. And it's interacting with the other hydrogen, which is a positive charge, at a distance of D plus L. Again, I have those distances labeled. D is the length of the hydrogen bond, and the L is the length of the bond within the dipole itself. Okay, and we'll have to do the same with the left end, OH, end of the dipole. So again, it's 0.35 E squared. And let's see, that OH is interacting with the other OH, so the charges have the same sign at a distance of 1 over D plus L. And it's interacting with the opposite sign, which is a negative potential energy at a distance of D plus 2L. And we're ready to evaluate that. I'll leave some intermediate steps, but we have K is 9 times 10 to the 9th newtons times meter squared over coulomb squared, and E is the fundamental charge. Okay, and putting that all together, the total energy of the hydrogen bond is just the addition of those two ends of the molecule interacting with the other one, and we get a common factor out front. And I'll put the nano means 10 to the minus 9. I'll put the nano in the upper exponent, get it out of the denominator. As you can see, all those distances are in the denominator. So there's an intermediate step just to verify if you're stuck on a calculation. And I won't put any more intermediate steps, but this is equal to minus 3.30 times 10 to the minus 20 joules. And that's per hydrogen bond. And this hydrogen bond has been attributed, the strong bonding in liquid water, which prevents it from being vaporized or boiled, has been attributed to this hydrogen bond. So what we would like to do is think through how much energy you have to add to break one bond is, of course, positive 3.30 times 10 to the minus 20 joules, the negative sign indicating that there is a bonding going on. But now we're going to try to compare this number to the latent heat of vaporization of water, which is a well-known quantity. It's the amount of energy it takes at the phase change between water and water vapor. And that's a very large number, 2.26 times 10 to the 6th joules per Kelvin. Sorry, joules per kilogram. Get my K's mixed up. Alrighty, so we know the energy it takes to break a bond, and now let's figure out the energy needed to break bonds in 1 kilogram. And that should give us something comparable to the latent heat of vaporization. So let's figure out how many bonds there are in 1 kilogram. So we're going to have to take the molecular weight of water, which is approximately 16 plus 2, 2 for the hydrogen, 16 for the oxygen, is approximately 18 grams per mole. Okay, and we can divide 1 kilogram by this to figure out how many moles we have, and then multiply by Avogadro's number. Convert the grams to kilograms. So we'll use Avogadro's number to figure out how many molecules there are in 1 kilogram. So this is molecules per mole. Oops, we lost our molecules per mole. Okay, and we work that out, and it is approximately 3.34. Maybe that's more accurate than I need, times 10 to the 25th molecules. And so the energy to break the bonds in 1 kilogram is the energy per bond times the number of bonds. And I'm just being careful to show all my little conversions there. And we wind up with about, what is that? 1.10 times 10 to the 6 joules per kilogram. Okay, we see that that is about the same order of magnitude as the latent heat of vaporization, which is not surprising. So that those hydrogen bonds are the ones that you're breaking as you're turning water into water vapor or boiling it. And probably what is off a little bit, why it doesn't give an exact calculation, is the idea that there is only one bond per molecule. There could be more. There could be less. So our model may be a little too simplified, but it does give the right order of magnitude.